go from current slide and get my pen color select. Okay. Any questions on anything we've done up to now? I asked the others, I'm pretty sure you too. You got the second test, right? Okay, good. So all of you have it. I've sent it to the other two. Okay. All right, where we left off on Chapter 4, Section 4.1. Chapter 4 is higher order differential equations. 4.1 is preliminary theory, talking specifically about linear equations. Okay. We just had talked about the difference between linear dependence and independence. If you have a set of functions, second, 4.1, page 121. Okay. Near the bottom of the page. If you have a set of functions, n of them, second, oh yeah, a set of functions, n functions here, and you combine them by adding, okay? And you can precede each one of them with a constant, any constant you want to. I'd say for now let these constants be real numbers. They use C's as if they could be complex numbers, but I'd just as soon not go into complex numbers if I don't have to. So let's let them be real numbers. And if when you combine these functions, pick a constant, any old constant to go with each one, and add them together, if that sum equals 0, okay, for any set of constants that you choose, except all the C's can't be 0, okay? So if you can have one or two, majority of the functions could be 0, but one or two are not, or none of them could be 0, the constant 0, and some linear combination of those. If you can make that sum equal to 0 without all the C's being 0, this is a linearly dependent set, okay? If you can't, if the only way you have a set, the sum of all those functions with constants multiplied by them, the only way you can get that sum to be 0 is if all those C's are 0, identically 0, then we say that set is linearly independent, okay? Not dependent, okay? Now, if you have two functions, just two functions, it's fairly easy to see whether they're dependent or not, okay? They give an example here, say of f1 of x is equal to x, the identity function. f2 of x is the absolute value function. Okay? Now, maybe I should do that in a different color. Y'all have a choice? Yellow, boy. Okay. The absolute value function would then be that one, whereas the identity function would be the other. So let me take out that one. Okay. Hopefully that's readable with his yellow function. Okay. That actually is not too bad. Okay. Now, on the set from minus infinity to positive infinity, if x can be that, obviously these are not dependent. Okay? There's no way you could get, if you added this function plus the negative of that, you could get 0. But then, no. Add this function to that function, you get a 0. If you did this, you get twice the function. Okay? So there's no way except 0 0. Now, if on the other hand, you were dealing with, say, from any interval from 0 to positive infinity, yeah, just set one of these equal 1, a constant equal 1, the other equal -1, or any two opposite numbers, and then those add to be 0. Or just add these two together. Let C1 equal 1 and C2 equal 1. This is negative, that's positive, those add to be 0. If you were strictly on this end, okay? But if you're on the whole range, no. There's no way those are linearly independent. But on the right-hand side, they're linearly dependent. On the left-hand side, they're linearly dependent. But they wouldn't be everywhere, okay? Now, so with two functions, you usually can tell almost by looking at it. And basically what you do is see if one's a multiple of the other. If they're multiples of each other, they're linearly dependent. If they're not, they're not. You get 3 or more, it's not nearly as easy to tell. Okay. So basically another way of looking at that would be if when you divide one function by the other function, if you get a constant, then they're linearly dependent. If you don't get a constant, then they're not. Okay. So let's do example 5. Wait, wrong. Okay. I'm going to get rid of my yellow if you don't mind. Okay. Okay. The set of functions, here's one, f1 of x is equal to cosine squared x. f2 of x is equal to sine squared x. And f3 of x is equal to secant squared x. And f4 of x is equal to tangent squared x. Okay. Okay, what we're going to do is look at that on the interval from -2 pi to 2 pi. I mean pi halves to pi halves. Now, when they say on an interval, that means you're using the parentheses here in interval notation, meaning starting with -pi halves, but not counting negative pi halves, and going to pi halves, but not counting pi halves. Any reason why that would be the case? Any between, but not the endpoints. Not negative pi halves, not pi halves. Any reason why they did that? Tangent and secant are not defined at pi halves or negative pi halves. Vertical asymptotes there on both of them. So you couldn't include that. So from negative pi halves to pi halves, yeah, cosine is defined, so cosine squared is. Sine is defined, sine squared is. Secant is defined inside of those, so secant squared would be 2, and tangent would be defined inside there. So tangent squared would be. Okay, now, the question is this a linearly independent or dependent set on that interval? Can you make that be 0 without all the coefficients being 0? You probably can easily, many ways, but here's the one that comes to my mind. What is sine squared plus cosine squared? Say again? Sine squared plus, say again? 1, exactly 1. So I know that, okay? So we know that sine squared x plus cosine squared x is equal to 1. Now, is there any relationship between secant squared and tangent squared that's also equal to 1? Second? You got it. Secant squared x minus tangent squared x is also equal to 1, right? So guess what? If I choose 1 times f of x, f1 of x, that's cosine squared, the 1 goes out here, okay, plus 1 times f2 of x, that's the sine squared x, minus f3, let's see, yeah, minus f3 of x, okay, plus f4 of x, I think I can get 0. Let's see if we can. These two add to be 1. The opposite of this adds to be minus 1, right? So it would be a minus secant squared plus tangent squared. That would be a minus 1, right? And plus 1 minus 1 equals 0. So there's 1. That's just a fairly easy one to get to. 4 coefficients, not all of them are equal to 0. 1, 1, minus 1, 1. Okay? None of them are equal to 0, in fact. And you can make the sum equal to 0. So that's a linearly dependent set, because you can come up with 4 coefficients, 1, 1, minus 1, and 1, to add to 0. Of course, you could also use minus 1, 1, 1, and minus 1. That would also do it. And any multiple of those, and probably many others as well. Okay? So yeah, that's a linearly independent set. So we let C1 and C2 equal 1, C3 be minus 1, and C4 be 1. And yeah, we got that. Second? Say that one more time. Yeah, that's the secant. See, what you have to do, this adds to be 1, those add to be 1, so if you negate this and that, they add to be minus 1, right? So when you negate that, that makes that a minus, but that makes that a plus, and then you have plus 1 minus 1 equals 0. So there's a linear combination of those 4 functions that add to be 0 without all the coefficients being 0. In fact, none of them are 0. That's linearly dependent. If the only way you can get that to be 0 is if all the coefficients are 0, that's linearly independent. Okay. Okay. And by the way, you can do this. Add that secant squared to this side, and then you have a new identity. Sine squared plus cosine squared plus tangent squared is equal to secant squared. And this would be sine squared plus cosine squared plus sine squared over cosine squared is equal to 1 over cosine squared. Multiply these kind of denominator would be sine squared, cosine squared. So have this is sine squared, cosine squared, plus cosine to the 4th minus cosine squared all over cosine squared. Sine squared over cosine squared is equal to 1 over cosine. Fiddle around with the numerators there, and sure enough you'll see you get them to be 1. We'll not do that. That was a trig problem. Okay. There is 1. Now, let's do example 6. Can we do it on the same page? Let's try it on clean, just in case we need more space. Don't think we will, but just in case we do. The set of functions, here's a new set, f1 of x is equal to square root of x, f2 of x is equal to square root of x plus 5x, f3 of x is x minus 1. Okay. Oh, you're right. F1 is square root of x plus 5. I didn't see the plus 5. Okay. The plus 5 is not under the radical. And F2 of x is square root of x plus 5x. F3 of x is x minus 1. And F4 of x is x squared. Okay? Now, what we want to know is there's some combination C1 times the square root of x plus 5 plus C2 times the square root of x minus 5x plus C3 plus C4 okay, equals to 0. Now, what we need is for not every one of the C's to be 0. Okay. Now, any first thoughts on this? This isn't nearly as easy as the last one, but it is not bad. Any thoughts, impressions as you just look at that? None whatsoever. Completely thoughtless. Okay. Okay. I look at that and say, I've only got one x squared term up there. There's no way I can combine any of the others that's going to make that x squared go to 0 unless that C4 is 0. But that's okay, as long as at least one of these is not 0. So I think C4 has to be 0. Can you see any way around it? You can't multiply these, you have to be adding them. So I think C4 has to be 0. Would you concur? Yeah, okay. Now, so I'm going to write that down. C4 has got to be 0. I may be wrong on that, but I can't see any way it could be otherwise. Now, the other thing that I see in here that keeps me from wiggling too much is we got 2 square roots of x's. And the only way you're going to be able to add those together if one of these is positive and one's negative. So that tells me that C1 has to equal negative C2. Do you see that? Okay. Now, I'm going to time out a minute and start and do it a little more rationally. Yes?
Shouldn't the C2 be x plus 5x?
Say that again?
Yeah, minus 5.
Okay, that was a plus. I've had trouble reading, haven't I? Yeah, that is a plus 5x. Okay. Ooh, a big plus, too. Okay. I'm going to do something slightly different. I'm going to multiply through and have C1 times the square root of x plus 5C1 is equal to, plus C2 times the square root of x plus 5x, 5C2x, I'll just do it that way, plus C3x minus C3. Did I get that one right? Yeah, I think so. Plus C4x squared is equal to 0. Okay. Now, what I'm going to do now is combine like terms. Is that okay? That'll be C1 square root of x plus C2 square root of x. That's got to equal to 0. And here we have 5C1 minus C3. That's got to equal to 0, right? C2x plus C3x has got to equal to 0. By that? And the C4 has got to equal 0. So that's where C4 has to equal 0, right? Now, all right. Basically, factor out the square root of x. And this says that C1 plus C2 is equal to 0. This says that 5C1 minus C3 is equal to 0. 5C2 plus C3 is equal to 0. I skipped, no, got them all, right. And we got that C4 is equal to 0. Right? Did I miss any? Okay. Now this might be a little bit easier to work with. Okay? Second, you could do a matrix, but not everybody has had matrices, right? So let me show you another way to do it. Add these two, and you get 5C1 plus 5C2. That adds a 0. That's equal to 0. And then at the top one, yuck, C1 plus C2 is equal to 0. Okay? That doesn't tell us much. You could divide everything by 5 there, and you'd be fine. But here we can say from this one here, we could say that 5C3 plus C3 is equal to 0. So what I would say is pick a parameter and say, this is 5C2. I don't know where that came from. So C3 is equal to 5t, or negative 5t. Okay. Let C2 equal t, right? That's where we'll start. Let C2 equal t, then C3 has to equal negative 5t, right? Okay? and see, then from this one, 5C1 minus C3 is equal to 0, but C3 is 5C1 minus 5T is equal to 0, so therefore C1 is equal to T. So C1 is equal to T as well. That's not right. I think it's minus T. If C1 is equal, if C2 is equal to T, C1 has to be minus T because of this, and then C3 would have to be minus 5T because of this one, and then C4 is equal to 0. Okay, so then pick a value for T, any one. Okay. I'm not going to use 0 because 0, 0, 0, you know, will work. So let's do T equal 1, so you'd have a minus 1, 1, negative 5, and 0. Okay? Let's see if that works. That would be a minus square root of x minus 5. Okay? Here you'd have a plus 1. So you have plus square root of x plus 5x. Okay. And C3 would be minus 5t minus 5. So that would be minus 5x minus 5. Okay. Let's see what we get. Yep. Minus, plus, minus. Whoa! No, that doesn't work, does it? Yeah, that's a plus here. Okay. Because it's CT is a minus 5, and you have minus 5x plus 5, yeah. So those go out, and these go out. So sure enough, that choice right there, C1 equal that, C2 equal that, C3 equal that, and C4 equal that. That would give you a linear combination of these added to 0 without all of them being 0. The C4 has to be 0, but the others do not. So, yeah, a matrix would have worked, but you can do it without a matrix because I knew not all of you had matrix algebra yet, linear algebra yet. Okay, but maybe you had done enough of matrices you could have. That would have worked too. All right, let's see what they said. They said, okay, did it slightly differently, but it works okay. They said F2 is equal to F1 plus 5F3 plus 0F4. Okay, so basically they said the C2 was a minus 1, C1 a 1, and C3 minus 5. Okay, they a positive 5. So they did it just with the opposite numbers. Okay, and it'll work. Okay. Linearly dependent or independent. Now, why are we doing that? I thought we were talking about differential equations, okay? Well, when you're talking about solutions of differential equations, we're primarily interested in linearly independent functions, or more to the point, linearly independent solutions of a linear differential equation. Although we could always appeal directly to whatever definition that was, 4.1.1, which is back there, it turns out that the question of whether a set of n solutions of inhomogeneous linear nth order partial differential equations is linear independent can be settled somewhat more mechanically by using a determinant. And Nigel walked out too soon, didn't he? Because he knows this, okay? And here we're talking about a Wronskian. And I'm not sure that all of you realize what a Wronskian is. Okay. Let's erase all this in. Okay. Let's suppose we have these n functions, f1, f2, f3, up to fn. And that each of those functions possesses at least n minus 1 derivatives. So if you have 7 functions, they must also all have the first 6 derivatives. Okay? Now, here's a determinant. You walked out too soon. Now we're doing determinants. Okay? But y'all have done them in physics. I think all of you have had physics. So here's the Wronskian of, it's f1, f2, f3, up to and including f sub n. N different functions. Okay? The Wronskian is this. It's the determinant of f1, f2, f3, up to f sub n. Those are the 4 n functions listed there. And then you'll do f1 prime, f2 prime, f3 prime, up to fn prime. You'll do f1 double prime, f2 double prime, f3 double prime, up to f sub n double prime. Okay? You'll this on down the page until you get to the f minus of the n minus 1, n minus first derivative of f1, f sub 2 of the n minus first, f sub 3 to the nth minus first. I can't write, I say first or write a fifth. Oh my goodness, my head's clogging up. Okay, all these are dotted, and a dotted, and a dotted down to f sub n to the n minus first derivative. Everywhere dot. Okay. Now, just something to pay attention to here. Obviously, we've got n functions. I was using 7 before, but whatever. Now, you have the function plus 6 derivatives, or n minus 1. So that means 7 rows. 7 columns, 7 rows. You can take the determinant of that. I don't particularly want to, but you can. Okay? Hopefully we'll be dealing with far fewer than 7, okay, most of the time. So there's different ways to take determinants, and Nigel can tutor you on this. He's got that knocked. We've done it in linear algebra. You're not? Yeah, you're in linear algebra too. Yeah. Now, okay, you got two helpers here. Both of them can lead you through determinants. Have y'all done any with determinants? I know you did with 3, but when you did cross products, you did a determinant. Same type thing, as long as you're 3 or less, you're fine. You can do the same type procedure you did there. When you get more than 4 or more, it gets a little messier, but you can still do it. Okay. All right. This is called the Wronskian of the functions. Okay? Now, here is the theorem that goes with that. Criterion for linearly independent solutions. If you have these, now they're changing and calling them y's. I don't know why, but why not? Okay. Y1, Y2, Y3, dot, 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 up to Y sub, are they still saying n? Yeah. N. These are all solutions, n solutions of a homogeneous linear nth order differential equation on some interval. Then the set of solutions is linearly independent. These are linearly independent if and only if, now there's a couple symbols for that. One is the double arrow. Another one is IFF, if and only if. It also means identity, friend, or foe in the military, especially in the Navy. The special beeper that every aircraft is supposed to put out, okay? So these are linear if and only if the Wronskian, this W of those functions, y1, y2, y3, dot, 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 up to y sub n. Okay. If this Wronskian is not equal to 0, it can be anything else in the world. Wronskian being the determinant. And Jonathan and Nigel, who have had this, know that if the determinant is equal to 0, then this is a what is the word for it? I'm going blank on it. Means it's not invertible. There's a name for it. But anyway, it's not. So, say again? Singular. It's singular. If it is equal to 0, it's singular. If it's not equal to 0, it's not singular. Okay. So that's another way of word for it. But we're talking linearly independence here. You got it. Okay. This is all you have to show. Hopefully you'll have 3 or fewer functions. Okay. They're easy with that. Okay. And that'll be true for every x in the interval if all those things are in the interval. Now it follows from that theorem that when y1, 2, 3 up to yn are n solutions of some differential equation, and their standard one they're using is back on the very beginning of the homogeneous section. This is on page 119. That set of nth order, linear nth order differential equation. Excuse me. That either the Wronskian is identically 0 or is never 0 on the interval. So either 0 or not, okay? The set of n linearly independent solutions of a homogeneous linear nth order differential equation is given a special name, and this is another definition, so I know I'm going to have new board for this. Any set and this will be y1, y2, y3, okay. Yeah, the eraser's not working. Okay. head's clogging up again. I don't know what it is. Sometime in the afternoon, and it did about mid-morning too. Just sort of like everything closes in. So any set you have here going up to y sub n of n linearly independent solutions of a homogeneous linear nth order differential equation on an interval I need to be writing some of that probably, okay. These are n linearly independent solutions of the homogeneous linear, so you got linear in here twice, one for the linearly independent solutions, but also linear nth order differential equation, DE, on an interval I is said to be a fundamental set of solutions. Goodness, I can't write. Okay, on that interval. Okay. What's that say? All right, you have a differential equation. Linear, nth order differential equation. Nth order differential equation. You come up with n solutions. Okay? But these n solutions have to be linearly independent of one another. And by the way, this is also a homogeneous linear nth order differential equation. Okay? On some interval I. If you come up with that, n solutions that are linearly independent, then you know that's a fundamental set of solutions. Any other solutions have to be some linear combination of that solution, because this is the most you can have. Okay? You can't find another one. If you've got n for an nth order, they're linearly independent, you can't find any more. Basically, that's kind of what it's trying to tell you. Okay, that's the fundamental set of solutions. Now, there's not just one fundamental set, you could have many, but they have to be, within that set, they have to be linear independent. The basic question of whether a fundamental set of solutions exists for a linear equation is answered in the next theorem. I think I'll leave that one on the board too. And that says there does exist a fundamental set of solutions for the, which was an easy way to write this, homogeneous linear nth order differential equation, okay, for that equation on that same interval. Analogous to the fact that any vector of three dimensions can be expressed as a linear combination of the linearly independent vectors I, j, and k, any solution of an nth order homogeneous linear differential equation on the interval can be expressed as a linear combination of the n linearly independent solutions. I just said that earlier, they're saying it now. In other words, n linearly independent solutions are the basic building blocks for the general solution for of that differential equation. Okay. I think I'll go to a clean page here just because this has a bit more writing on it. Good. So let's say we have y1, y2, y3, up to and including y sub n. They're a fundamental set of solutions. Now, if they are, that means they're linearly independent of each other. Okay? Of the homogeneous, linear, nth order, differential equation on the interval I. Okay, tired of writing all this. Then the general solution of the equation on that interval. So that's the fundamental set. The general solution of that differential equation is this. Y is equal to C1. Why would they use Y? But I guess it's okay. Y1 of X plus C2, Y2 of X plus C3, Y3 of X plus ... up to and including C sub n by n of x. Okay. Where these C's, C1, C2, C3, all the way up to C sub n are arbitrary. Okay. And they're all constants. Now, they never have said whether they're restricting them to real numbers or allowing them to be complex numbers. Quite often when they use C's, they allow complex, but we're not. Let's assume we're staying with real numbers for now. Okay? Now, what this states is that y of x is any solution of your ordinary differential equation that we have there on the interval, then the constants states that y of x, capital Y of x, is any solution that then the constants C1 through Cn basically, trying to think of a simple, straightforward way to say that. If you find such a solution, if y of x is any old solution, you just know it's a solution of that differential equation on the interval, then you can come up with some linear combination of that fundamental set and have it. And the C's, and why they went to capital C's here, I'm not real sure, but it's fine. They're just constants. And by the way, all those C's, they can't be zero, obviously, unless y of x is just specifically 0. They do it for the case of n equal 2, which is a pretty simple case. But since some of you have not had determinants, trying to see if one of these examples would be a reasonable one to do. Okay, let's just go on to example 7. I don't see that there's a lot of benefit in trying to do those that all they have are letters and you can't really do much with them. So let's go to example 7 and erase this ink. Man, my throat is so scratchy right now. I think I can make 20 more minutes. It's not going to be easy, I don't think. But here's one. Here's two functions. y1, e to the 3x. Here's a y2, e to the minus 3x. Okay? Now, they're telling us both of these are solutions of the homogeneous linear differential equation y double prime minus 9y is equal to 0. On the interval minus infinity to infinity. Okay. Okay. Now, actually, a couple things we really should do. You should verify that that does fit the equation. And that's not hard to do. How would you do that? Take a derivative. y1 prime would be 3e to the x. y2 prime would be negative 3e to the negative 3x. Okay? What's that? Right? Oh, 3x. It is. I'm sorry. I just left that out. Okay? y1 double prime, we need that too because your equation has it. It doesn't even have the y prime in it, but it does have the y double prime. What would that be? 9e to the 3x, and y2 double prime is 9e to the negative 3x. Okay? Now let's make sure both of those fit the bill. If you take this equation here, multiply it by negative 9 times that one, sure enough you get 0, right? Negative 9 times that one, right? If you take this one here and multiply it by negative 9 times this one, add those together, sure enough you get 0. So both of those are solutions for that differential equation for all real values x. Okay? Now we didn't have to do that, but just yuck, don't tell me I just did that. Yuck. I went to erase and erased too much, and it won't go back. Yuck. So I have to write it again. Okay, sorry. y1, goodness gracious, my throat, is equal e to the 3x, and y2 is equal to negative e to the 3x. Okay? That's our solution we just found. We verified for y double prime minus 9y equals 0. On minus infinity to infinity. All real numbers. And that is, by the way, a homogeneous because it's equal to 0, linear because each of those is the first thing. What else? Differential equation, right? Okay. Now, what we haven't done is see if they are linearly independent of each other. Something sort of smacks of them. They look so similar. And by the way, Yuck. Y'all didn't catch me on this one. It's a minus 3x, not minus e to the 3x. Right? Okay. Yeah. Okay. That these are not. But there is a fairly easy way to tell if they're linearly independent or not. And that's through the Wronskian. Now, I just had the thing, so we're going to have to do it again. The Wronskian is the determinant of the functions e to the 3x, e to the minus 3x, and the first derivatives, because you do it 1 minus whatever your order is, in the order minus 1. So this will be 3e to the 3x minus 3e to the minus 3x. Okay? Now we take a determinant of that. Anyone remember how to do a determinant? I know Jonathan does. Remember? Yeah. Okay. It's the down diagonal, the main diagonal, the product of those minus the product of the up diagonal or the other one. Okay? Non-primary. Okay? So let's see what that is. That is the product of this and that, e to the 3x times e to the minus 3x. So that's e to the 3x times a minus 3 e to the minus 3x. Minus, and it doesn't matter which order, e to the minus 3x times a positive 3 e to the x. Okay? 3x. Okay. Now, goodness, my throat. Let's first multiply e to the 3x times e to the minus 3x. What is that? This is e to the 3x times a minus 3. Now, I'm going to write that e to the minus 3x as 1 over e to the 3x, right? Ding, ding. Notice the sound effects, okay? Minus e to the, well, this is 1 over e to the 3x times 3 times e to the 3x. Ding, ding. Okay, again, they went out, and you get minus 3 is equal to minus 6. And as long as this is not 0, that means that you got linear independence. Right? That's all it takes. As long as that Wronskian, that determinant, is not 0. If it is 0, they're linearly dependent. If it's not, they're not. It doesn't matter what the number is, positive, negative, fraction, decimal. Doesn't matter as long as it's not 0. Okay. Okay. And that's true for every x out there. Okay? So what can we do with that? We found two solutions. It's a second order differential equations. Those two solutions form a fundamental set, right? Because they're linearly independent. You don't need, and you don't need to come up with or try to come up with any more. They're none more, okay? You could come up with two different ones, but those are it for this set, okay? So therefore you can take, and our general solution will be y is equal to any old C1 e to the 3x plus any old C2 e to the minus 3x. Just take those two functions and add any linear combination together. You have your general solution for the differential equation on that interval. That's it. Can't come up with any more. Every solution can be made as a combination of those. Okay? Let's try example 8. Oh, man. Wow. And frankly, I don't care for hyperbolic signs and cosines. Do y'all have a preference on that? I know. They're almost a mathematical invention. And they're kind of a handy little invention, but frankly, I'm happier dealing with exponentials. And all they are combinations of exponentials, okay? So I'm kind of in favor of just skipping that one, okay? Yeah. No. I was thinking they may have something in here to help you with it, but I don't see them. So I'm not going to look for it. What gets me with this example, notice that they say this is a solution, and they go through all this stuff, and the last expression is recognized as the first expression. I think, were you supposed to have proven something there that it's equal to itself? So let's just skip that. Let's go to example 9. Yeah, much nicer. Here are some functions. Here's a y1 equal e to the x. A y2 equal e to the 2x. Here's a y3. Guess what? It's e to the 3x. Okay? And it says those three functions satisfy the third order differential equation y triple prime minus 6 y double prime plus 11 y prime minus 6y equals 0. Linear, homogeneous, linear, third order differential equation. They've given us three solutions, which should be all that you need. We ought to quickly check and make sure they are indeed solutions. y1 prime, I can do this one, e to the x. y1 double prime, I can do that one, e to the x. And y1 triple prime, I can do that, e to the x. Okay? That was easy. You get to do the others. y2 prime, 2e to the 2x. Okay? y2 prime, double prime, is equal to 4e to the 2x. And y3 y2 triple prime, I got my 3's and 2's crossed up, is equal to 8e to the 2x. y3 prime is equal to 3e to the 3x. y3 double prime is equal to 9e to the 3x. And y3 triple prime is equal to 27e to the 3x. Yay. All right. Now, we need to do this for all three of these, but I think it is. All right. The first one is really easy, because all those are the same. So basically we have 1 minus 6 is, all those are e to the x's. So I'm just going to put e to the x and e to the, that would be 1 e to the x minus 6 e to the x would be minus 5 e to the x plus 11 e to the x would be positive 6 e to the x minus 6 e to the x would be 0. Yeah, that was 0. Okay? Now, let's do this one. 8 minus 24 would be minus 16, right? Plus 22 would be plus 6, minus 6, that's 0. Okay? Now the hard one. 27 minus 54 would be minus 27, plus 33 would be minus 6 plus 6 minus 6, 0. I hope I did that right. I think I did. Yeah. Plus 6 minus 6 equals 0. Yes, we verified it. Those are three solutions. Okay. All we have to do is make sure that those are linearly independent. We know they all satisfy, but we don't know that we're linearly independent. That's where the Wronskian comes into play. The Wronskian would be, I'm glad I left these up here, e to the x, e to the 2x, e to the 3x. E to the x, 2e to the 2x, 3e to the 3x, and e to the x, 4e to the 2x, 9e to the 3x. Okay. Remember how to do the 3 by 3 determinants? Huh? Either of you, since you're only 2 in here. We can just repeat these first 2 columns. There. So let's take away this and repeat the first 2 columns. Now this may not be the I think it is the easiest way. E to the x, e to the x, e to the x. That was easy enough. E to the 2x, 2e to the 2x, and 4e to the 2x. Right? Now, down diagonals, when I multiply these together, that gives me 18. Now, that's the numerical part. And when I multiply those together, I add together my exponents, right? So that'd be e to the 6x, right? Then I'll do this down diagonal, okay? Plus 3, that's my coefficient. And my exponent is e to the 6x. Okay? Then I'll do this down diagonal. It's not quite diagonal, but close to it. And that would be plus 4. And that comes up to e to the 6x. Okay? Now I do my up diagonals. And what's that? I'm sorry, I can't hear.
No, it's just the way it's written. We'll multiply together.
What's that? I can't hear.
No, I mean, I can tell we multiply together.
Oh, okay. I'm multiplying first the coefficients.
Yeah,
One,
no, I'm talking
two.
about on the end.
The last one?
Yeah,
is 4.
I didn't see that.
Okay. And then e to the 2x times e to the x will be e to the 3x times e to the 3x will be e to the 6x. Same bases, multiplying the bases, you add the exponents. 3x plus x, 2x, 6x. Which is sort of good. They are all like terms. Now I'm going to do the up diagonals, and these will get subtracted. So that's a minus 2 e to the 6x, right? That up diagonal is going to be a minus 12, because it's going up, is minus 12 e to the 6x. And the last one is going to be a minus 9 e to the 6x. Okay? Okay, you missed.
So the power should be multiplied or the add?
Okay. If you have what would that be? Fifth, you add the exponents. Because this is x times x, that's x times x times x, that'd be x to the fifth. Yeah, yeah, you're adding the exponents. Right. Okay. Now, we've got those done. Let's add the positives. That's 22 and 3 is 25.
I got it.
Say again?
No, I just put it in the calculator.
Oh, okay, yeah. That's 25. This is 21, and 2 is 23. So that'd be 3e to the 6x. Right? Is that what you got? 2? Okay. I can't. 23, 25. Yeah, 25, and that was 23. Yeah, 2. So that gives us 2e to the 6x. You know, I don't care what x you put in there. That's going to be a non-zero number. Because e to the x is never 0, and 2 is never 0. So you don't care what it is, you just know it's not 0. For any x you put in there, it's never going to be 0. Okay? So, you have, number 1, shown they all satisfy the differential equation, and they're linearly independent. So therefore, your general solution would be some linear combination of that. Y is equal to C1 e to the x plus C2 e to the 2x plus C3 e to the 3x. Every solution to that can be written in that form. Okay? Oh my, it is that sad time, isn't it? We'll begin next time with 4.1.3, bottom of page 124. Homework exercises here. I've given some of these before. Do either 1 or 3 or both. Either 5 or 7 or both. Either 9 or 11 or both. Do 13. That was 4.1.1. 4.1.2, any of the odds 15 to 21, and any of the odds 23 to 29. I think those are the new ones that we haven't done. Okay. And we'll pick up with 4.1.3 next time. All right, sadly, y'all have heard it, right? Good news, bad news? The good news is that next week is spring break, but the sad news is we won't see each other all next week. So, get over it. Okay. No class. But plenty of things to work on for homework, right? And tests. And write the paper. Good idea. Okay. Yeah, you've already turned in your research paper, didn't you?
Oh, I did.
Yeah. But you didn't turn on one for him. That was the problem. Okay, yeah. All right.